So we're looking at theorem of perpendicular axis. So before I go to the theorem itself, let me talk about one thing. Say I have an object or say a point, and this is a distance. Let me call this as r. So my question to you guys is, how can I figure out the distance given I know the projection of this point onto x and y axis? So this is x unit and this is y unit. So my question is, how will we figure out r? So obviously this is also x, this is also y, and you know that this will be 90 degree. So from figure, r square is equal to x square plus y square. So where did I get this from? Pythagorean theorem. Okay guys. Now imagine that we have a flat surface, and on this flat surface is this point. Okay. So we have, let me actually change the color. Not happy with that. Say we have some flat surface and this point is on this flat surface. Right guys? So now let's go to the theorem. If you know how hard it is to spin an object in one way, you can figure out how hard it is to spin it in the other way without doing more fancy math. You'll see the answer actually. This essentially, this is basically the theorem of perpendicular axis. So your statement is, for a planar object, the moment of inertia about an axis perpendicular to the plane is the sum of the moment of inertia of the two perpendicular axes through the same point in the plane of the object. Okay, it's kind of weird. So let me go to the proof itself. So we are considering plane lamina lying on the XOY plane. Okay. So it's made up of large number of particles, because I started with particle, right? So this is particle P at x comma y with mass m. Large number of particles. Then what else can we? Okay, we'll start off with, let's consider one such particle of mass m situated at Px comma y. So from figure, this is part of the derivation. From figure, r will be equal to root of x square plus y square. Now, if I am rotating this object, okay, so we have moment of inertia of the particle about x-axis. Okay guys, so if this is the rotational axis, let me actually go over here, it'll make more sense. Say I have this as axis of rotation, I have this particle. How much is this length is my question. What is this length? Yeah, what is that length? Remember, this is x-axis. This will be y, is it not? See, this length is y. That's important for us to know because many people get confused. So this, from this axis, x-axis, the distance to the particle is y. And so moment of inertia of the particle about x-axis is my square. Then you have moment of inertia of the particle about y-axis would be mx square. Okay, right? Now, if I have to figure out the moment of inertia of the whole lamina, okay, so this is first two things. Then we have moment of inertia of all the particles, basically, of all particles would be what? Particles along x-axis will be what? Well, I can call it as Ix. This will be equal to summation of my square. Right? And next, you have similarly moment of inertia of all of this along the y-axis will be what, guys? Iy, which will be equal to summation of mx square. Then, now, the final thing, moment of inertia of particle or all particle or you can call this as whole lamina along z-axis will be what? Well, in a similar line, it will be equal to mr square. The same funda, is it not? Nothing fancy happening over here. First we saw for 1 and then we moved on to the whole lot. But what is r? R is nothing but x square plus y square, r square, sorry. R square is nothing but x square plus y square. This is from 1. Okay, so I'm calling this as 1. Where is 1? Just a second. This is 1 for me. And now if I just use our distributive property and I have mx square plus summation of my square, and your moment of inertia along the z-axis is along the x-axis plus, oh sorry, this is y-axis and this is along the x-axis. And that's what your theorem is trying to tell. If I can figure out the moment of inertia about two axes, all I have to do is just add them up and I'll get the moment of inertia of the third axis. Let's look at the statement again. For a planar object, so first thing is I need to define a plane lamina. I kept using that, but I didn't define it. A plane lamina is a flat two-dimensional object with uniform thickness or mass distribution. You need to understand that you have to have this as the standard object that is under rotation. If not, we can't use it. A plane lamina is a flat two-dimensional object with uniform thickness or mass distribution. Keep that in mind. So for a planar object, the moment of inertia about an axis perpendicular to the plane is the sum of moment of inertia of the two perpendicular axes through the same point in the plane of the object. So again, I know you guys got it, but still for my satisfaction, say I have some object like this. This is it's plane, uniform thickness and everything. So if I'm rotating along this point, and this is your axis of rotation. So along that same point, if I know I might not be successful in doing the right diagram for this actually. It would be something like this, guys. And here, I guess. Yeah. if I have something like this scenario, if I know the moment of inertia along, say, y, not y, I want to call it as a axis, and this I'll call it as b axis. So if I know how much I have to struggle rotating this object along the a and along the b, I'll be able to figure out along the c axis. Of course, if I know a and c, I can figure out b. If I know b and c, I can figure out a. It's simple math, but point is, you need to have all of these conditions satisfied. So through the same point, right, somewhere along here is the point wherein all of this will pass. So that common point has to be there. I can't have some axis over here and I can't figure it out in that way. No, it has to be so. And it comes from a simple fact that r square, that is Pythagoras theorem. Pythagorean theorem, you have r square is equal to x square plus y square. So if you understand this, you pretty much understand this. Okay. So let me see if I didn't miss anything. How do you use it? It's a valuable tool in building up the moment of inertia of three-dimensional object such as cylinder. How? By breaking them into planar disk and summing the moment of inertia of the composite disk. So you can see that it leads to learning this can help us in moving up to a complicated structure. Like slicing things up, getting one aspect and then summing it up. So for that, we'll use different mathematical tools. So that's the whole funda. Yeah, now you guys can write all of this. And as a proof, you guys should be writing this.